My name's Adam Denenberg. I'm the current VP of Engineering at the Huffington Post. And my talk today is going to be a little bit about our journey in terms of embracing Erlang for our use of WebSockets, SockJS, and RabbitMQ. So I'm going to be talking about a couple projects that we used at the Huffington Post. Our first project was something called HUFFPOST Live, which is a live video streaming network that we built a little over a year ago. And that was sort of our first embark in terms of Erlang for the engineering team. And we've kind of expanded a little bit from that learning into a new project that we call OUTBREAK that hopefully we'll be open sourcing within the next couple months. And just going to kind of talk through the architecture, how we use RabbitMQ for building sort of this pub-sub real-time commenting system at the Huffington Post. Just a little info about the Huffington Post itself. For those not familiar, we are a very large social news website. We've expanded domestically. We have instances of the Huffington Post in a bunch of countries around the world now: France, Italy, Spain, Canada, the UK. We're launching Germany next week, and that's continuing to expand. About 77 million unique visitors globally per month, and commenting, obviously all of our articles have comments attached to them. We're over 250 million comments. I think we're on track for about 300 million before the end of the year. And editorially, we publish about 1,600 articles a day across the platform. So when we talk about our journey in terms of building a real-time commenting system, there were some obvious choices that we looked at when we started. Node.js, Socket.io. I think Alex gave us a pretty good background on some of the Node stuff. SockJS, which is a lot of what my talk about is today, was one we came across. Looked at EM WebSocket. We were using still are a fair bit of Ruby in the application. CometD, and there's pretty much an infinite list of real-time WebSocket polling frameworks out there. These were a few that we started looking at. So not to get too ideological about all of it, but a little bit of our research. When we started evaluating the different options, different frameworks that we wanted to use, this was some of our experience. When we look at like WebSockets, big thing for us also was supporting a lot of browsers. So we couldn't just say you had to be on an HTML5 browser. We did have to have support for older IE8 users across the world. So just supporting pure native WebSockets wasn't really sufficient. So we looked at Node.js and Socket.io, and I won't really get too much into the Node ideology. There are some issues with Socket.io in terms of requiring Flash for upgrading the protocol. There are, and again, this may have changed. This is kind of going back a while when we looked at it. But at the time, Socket.io did have a sort of shared state requirement, and I think it was only even Redis was supported, making it a bit more strict. So there was this sort of persistent backend requirement. We weren't really crazy at the time about the maturity of Node in terms of some of the concurrency story. JavaScript is single-threaded. I know that we can get multi-core performance out of Node, but there was a lot of talk around running one instance of Node per core. All this kind of stuff. And also, Socket.io was actually evolving into Engine.io, so they were kind of taking a more holistic look at where Socket.io was evolving to, and I'm not even sure the current state of Socket.io. I think a lot of the mechanics are now in a more lightweight, transport-focused Engine.io. We looked at EM WebSocket. We were using a lot of Ruby in our app, so we sort of naturally just looked at some Ruby solutions out there. Honestly, we just didn't feel that Ruby was a great language for a concurrency story, so we didn't really invest a ton of time. CometD, the WebSocket support wasn't a great story there either. There really was kind of only, I think, a long polling option at the time. The WebSocket support didn't seem fully baked. So, our research was, had us kind of questioning that. Then we came across SockJS. So some things we liked about SockJS, and a lot of the talk today will kind of go into a bit more detail as to why these things are important for us and why I think they're good in general. Number one, no Flash fallback. So Socket.io requires Flash. We didn't want any Flash requirement for downgrading browsers that didn't support WebSockets that had to go to XHR polling, JSONP, whatever the other transports were. The JavaScript library did all the detection automatically, which meant we didn't have to worry about writing all of this logic in terms of figuring out which browsers supported which transport protocol. The SockJS JavaScript library just kind of knows what the browser supports and auto-degrades for you. And what we'll go into in a bit is we'll see that, SockJS sort of emulates a WebSocket protocol. So you can write your application the same regardless of how the browsers communicate with the back end. And SockJS just handles downgrading the browser automatically for you, which is really nice when you have a broad set of browsers to support like we did. Again, no change in code for the browsers. And native WebSocket client support, this was important for us for mobile. So SockJS is a JavaScript library. So we did have to sort of ask the question around, okay, so what happens when we build our iOS applications or our Android native applications? So since SockJS does emulate the WebSocket protocol, you can actually connect a native WebSocket client directly to it. There are a couple caveats that I'll talk about, but out of the box, it works. We have it in production now for our applications, and it's quite stable. And another big one for us is more architecturally, the way SockJS actually implements itself is the way that it supports load balancers and not having any kind of shared state. So I talked before about how like Socket.io had this Redis persistent backend requirement where it had to keep track of which users on which node. The way SockJS is set up is it's really easy to get linear scale. There's no shared state. The state is isolated to a single node in the cluster. So obviously our decision, SockJS, tested in using native WebSocket clients, as I mentioned, in our native iOS apps, worked with our load balancers, and again, linear scale, no shared state. This was a really, really nice win for us. We didn't want to have to depend on another persistent backend to try to keep track of which users were on which node and do cross-node communication. Being able to just kind of add more nodes as we either wanted to deal with more concurrency or reduce the message latency was really kind of a nice, easy win from an engineering standpoint and also just from an operational standpoint. So just to sort of read verbatim of how SockJS defines itself, SockJS is a browser JavaScript library that provides a WebSocket-like object. SockJS gives you a coherent cross-browser JavaScript API, which creates a low-latency, full-duplex cross-domain communication channel between the browser and the web server. Basically, under the hood, SockJS tries to use native WebSockets first in terms of its protocol order. If that fails, it can use a variety of browser-specific transport protocols that use WebSocket-like abstractions. Again, SockJS essentially emulates the WebSocket protocol and uses it as a transport and handles the actual implementation of the type of transports you use, whether it's native WebSockets, whether it's XHR polling, JSON-P. So basically, it just kind of handles that channel communication for you. So let's talk a little bit about the load balancing, which was kind of a really nice feature for us. So if you run Firebug or whatever tool you're using to sort of inspect the HTTP request, you'll see a request that looks similar to that session URL above. So basically, what you'll see is a URL prefix, which is any predefined prefix you write in the Erlang side of things, server and session. So server and session are kind of the important ones here. So basically, the session is initialized by the client, as it mentions here. So the client chooses a server ID, which essentially is a 3-digit number from 0 to 1,000. It can be supplied by the user, randomly generated. And basically, the main reason for this is to handle sticky sessions. So you'll end up with a URL that looks something like this, where you have your prefix, you have your server ID, then you have your session ID, and then the last element here is basically the type of implementation. So depending on what your browser supports, if you're on, say, IE8, you'll probably see something like XHR polling here. If you're on Chrome, you'll see WebSocket. So what's really nice about this design pattern is in your load balancer, you can basically do URL hashing. So what that enables is that since a user, when I make a connection, I'm going to leverage the same URL from my session, I can use URL hashing in the load balancer. I can bind you to the same node. And now I know that, okay, so user Bob is now bound to server 3. I know that every HTTP request he makes is going to get routed to the same node every time. And this makes it really easy to kind of handle linear scale. There's no risk of my next connection may hit a different server, and now I need a sort of hash table in the back end that I have to query to figure out which node that user is on, and then I have to route messages based on where that user lives. We just use simple URL hashing through the load balancer, persist that user to that box, and then this kind of model just makes it very easy to just sort of add more nodes to scale horizontally. So some challenges as we got going. for one, nobody knew Erlang, which is, I guess, always eventually a problem for someone, in theory. And we didn't have a lot of time. So we did a lot of research. We looked at like the C10K tests and all this cool stuff. We were really comfortable and confident in our decision that Erlang was the right tool for the job. However, we were kind of like scratching our heads and said, okay, so like, where do we start? Do we just go buy a bunch of books? Like, what do we do right now? So it was a challenge, but we embraced it. We had 4, maybe 5 months to build the whole platform, and I'll show some screenshots in a second. The native support for WebSockets, we were using, still are, NetScalers, was kind of beta at the time. So a little bit of a risk in terms of WebSocket support. I do believe there's pretty fair use of HA proxy out there for Sock.js, so that shouldn't be an issue for native WebSocket support. I think Nginx as well has some pretty good WebSocket support now, so those are some other good open source options. And message latency. So when we were looking at our use case, specifically for HuffPost Live in our first project, it was less about throughput, and it was really more about latency. And I'll kind of show the visual in a second, but our big concern was when a producer or someone actually published a message, that every user was getting messages very quickly. And again, our model was basically low throughput, but low latency. And we really didn't know if it would work, as I mentioned. So we took a chance, we took a gamble, but that's what it's all about sometimes. So what is HuffPost Live? HuffPost Live is a 9-hour live streaming network that is sort of a sister project of the Huffington Post. And the idea with HuffPost Live was essentially to bring those 250 million comments into a live streaming conversation. So you'll see in some screenshots, basically, we do about 20 to 30 live segments per day. From our New York studio. We're expanding a little bit internationally there as well. And basically the whole idea was to have this real-time comment stream living next to the video. We have a traditional, fairly sizable production team producing all this content. We wanted the ability for producers to sort of push content in real time below the video player. So a use case there is, someone comes on the show, say it's, I don't know, Brad Pitt, and he said something completely ridiculous, and one of the producers wants to go to Wikipedia and just either counter or support something he said. We wanted to give them the ability to go to the CMS, publish a link in real time to the video player, have it show up to the users without anybody having to refresh. So I'll show in a second that browser refresh was really not an option for all the mechanics that we needed for HuffPost Live. It's a traditional sort of single-page application using Backbone, and there's really not a lot of browser refresh happening, and a lot of what drives the application is happening in real time. And lastly, as I mentioned, we just couldn't guarantee everyone was on HTML5. We couldn't just send all the IE8 users and older Firefox users a sorry message and tell them to upgrade. We had to support non-HTML5 browsers with this real-time requirement. So this is kind of a screenshot of what HuffPost Live looks like, and I kind of boxed out some of the real-time components. And if you include the video player, there's really not a lot left that's not real-time. So over here to the right is sort of the real-time comment stream. So this is just sort of our custom version of a Twitter stream where people can have a real-time conversation alongside the video player. Up top is our segment navigation. So we'll be watching, I don't know if that's Lisa Kudrow, who that is. The Novak Djokovic Foundation is on. There's a traditional studio. A producer is going to push us to the next segment as soon as the next host is ready, and that allows you to have sort of this lean back experience where we don't just say, hey, the next segment is live, go click on something. If the internet was working, I would show, but basically you'll see this whole screen will just sort of transition in real time to the next segment as it's being controlled from the studio. And then below the video player there is what we call our resource well. So there I can push tweets, videos, links to stories in real time from the control room. So you'll see here, like, a lot of what we post live was all happening in real time. Just a quick, this is our tech stack for HuffPost Live. So we used a fair bit of Ruby and Rails for some of the CMS and APIs. Backbone.js was driving a lot of the client-side UI there, so a lot of single-page application stuff going on. Erlang, obviously, we're using for all of our WebSockets. We actually also built this AMQP bridge, which I'll talk briefly about, which was essentially just bridging two RabbitMQ clusters. Mongo for our database, Memcache for your standard DB caching stuff, and Varnish for some Edge HTTP reverse proxy caching. That's a high level of our stack for HuffPost Live. Quick slide on comments. So I mentioned, we have the 250 million comments on HuffingtonPost.com. We have the real-time comment stream. So comments inside of Huffington Post are actually treated like a service, similar to Discuss or Livefire, if you guys are familiar with some of these commenting services. So we have a lot of internal technology that does comment moderation. So whenever someone submits a comment, even on HuffPost Live, it actually goes into our internal commenting platform service that we have internally at HuffPost. We have some machine learning technology that will do some NLP and analysis of the comments, do some abusive detection, and then we have a moderation queue. So we have a bunch of comment moderators that will look at anything that our NLP technology is essentially unsure about and will manually approve those comments. So resources below the video player being pushed and reordered in real time. So again, that was a production control below the video player. And basically, there were essentially various inputs to a message. So we really needed something generic, right? We had all these different use cases with segment transitions, with comments, with real-time links and videos getting pushed below the video player. We needed something very generic that can handle all these different use cases. So just to talk real quick about the AMQP bridge. I'm not going to talk too much. This is another Erlang app that we have, but just to talk about it. So I mentioned some of the comment moderation that we have. So every comment, even on live, goes to this sort of comment service we have in the back end. Essentially what happened, and it just kind of worked out nicely, is that the comment platform actually leverages a lot of RabbitMQ as well. So what happened was we essentially built this AMQP bridge, which is a really light Erlang application that has basically two gen servers, a producer and a consumer. And one gen server essentially subscribes to the commenting RabbitMQ topic and just listens for messages as they get either auto-approved or manually approved. And then we have that's the consumer side. And the producer side that essentially pushes those into our WebSocket infrastructure. So if you guys are familiar with RabbitMQ, there's a tool called Shovel, which essentially does this, which moves messages between RabbitMQ instances. The only reason we didn't use Shovel is we had to do some sort of JSON transformation and massaging of the data, and that was just a little bit easier for us to do at the application level. But it was a pretty interesting experiment in terms of having a really nice little AMQP glue that we built. So I just wanted to talk about this quickly because this was another Erlang application that we had to build internally. So the CMS workflow. So this was, again, a big input to messages in the HuffPost applications. So as I mentioned, we do have a traditional production team. So, we even have some patents that are gotten published around this, but usually in a traditional studio, you see a lot of buttons and levers, and it's a lot of old school wires and cables, and things are like very connected. It's very rare you'll see someone in a control room with a laptop and a browser. We sort of took that whole model and flipped it on its head. We actually have all of our production capabilities outside of like camera controls and things like that living inside of our CMS. So controlling things like a rundown, if you guys watch the newsroom, controlling notes, prompter scripts, guest information, all this stuff is actually controlled inside of our web CMS, which is very non-standard for a traditional production team. So what that meant is we had to give the production team the tools to make our web CMS act like a traditional set of studio tools. So transitioning segments for a live stream was happening from our web CMS. All of the comments were happening through our web CMS. Pushing information below the video player was happening from the web CMS. So, there's a supervising producer that sits in the control room, has their CMS open, and needs to control essentially what everyone in the world is seeing in real time on HuffPost Live. So, basically our CMS basically became this way to essentially control state of the application. So literally with one button click, a producer in a control room can transform in real time for everyone what everyone sees on HuffPost Live, which was a pretty interesting experience. And on the Ruby side, just a note, we were using AMQP event machine inside the Ruby side to push event machines into Rabbit, basically. So this was kind of our CMS workflow, which was a big contributor of real time. So this was all great. things were successful, and one problem. We started realizing that we wanted to actually reuse what we were doing for other projects. So we had such good success. The problem was we ended up with this HUFFPOST Live specific monolithic Erlang application that no one else can just kind of take and say, oh, hey, great. I like what you guys are doing with PubSub. I can reuse this for use case A or B. So we started thinking about how we move forward now that we realized we demonstrated that SockJS and the Erlang app was successful. We got good scale. We got good stability. So we started figuring out how we can decouple things and say, okay, we want to basically extract just the WebSocket plumbing, right? We got to take out some of the application specifics that HUFFPOST Live needs, whether it's messages you skip or JSON transformation, and just take out the WebSocket plumbing. So this led to essentially what we now call internally OUTBREAK. So the idea behind OUTBREAK was to remove the core of the WebSocket logic into its own app and just make it a library. So every new application that we have internally essentially just includes OUTBREAK as a library in rebar.config. And then basically what we did is to sort of abstract things away, we created these callbacks. So these callbacks essentially give you certain checkpoints into the data flow. So init is when a user connects. So say you want to wire up some custom authentication, or you want to check a user's client IP address, or whatever it is, right? Init can give you sort of that interception layer. Close is when a user disconnects. Maybe you need to clean up some external database somewhere, or purge a session in some other system or whatever may have you. So close is sort of when users disconnect. Messages is essentially when OUTBREAK has consumed the message off the RabbitMQ topic. So when we get a message, we may want to discard certain messages. We may want to transform certain messages. We may want to query an external database and join that message with additional data, whatever may happen. And then receive is a message initiated from the client. So we may want to expand the existing support that OUTBREAK has for subscription and unsubscription to channels. So receive is, and I'll talk in a sec about our JSON payload structure for subscription, but receive is basically messages initiated from the client. So just some bullets, concept and guidelines when we built OUTBREAK. Number one, and most importantly, keep things very generic. We don't want to prescribe any kind of data flow or any kind of business logic. Keep it very generic. Consumers wait for messages for the channels they're subscribed to, and then producers send messages to a predefined RabbitMQ topic using a specific routing key. That's really the guts of what OUTBREAK is. We leverage routing keys, which I'll talk about very heavily in terms of matching up channels and IDs and subscriptions. But that's kind of fundamentally what OUTBREAK is doing in this PubSub world, is bridging the consumers and the producers with some application logic. And really fundamentally, the way OUTBREAK is built is consumers and producers really shouldn't know or care about how messages are getting there. If I'm a consumer and I'm waiting for comments and I'm HUFFPOST Live, I don't really care how the comment got into OUTBREAK. I don't care if it read a file, if it was an HTTP call, if it was a RabbitMQ message. It doesn't matter, right? A message needs to get into OUTBREAK. OUTBREAK figures out who that message is destined for, and then it broadcasts it out to whoever's listening. So fundamentally, we just have to say, okay, how do I know what you're interested in, and how do I get a message? And then OUTBREAK becomes essentially this router. So Fiji was our first project to leverage this new model called OUTBREAK. So what Fiji is essentially this internal activity stream. So what we did is we built a really simple API where you could submit events to. We use Storm, which is a product from Twitter, which basically handles a lot of, it's kind of a real-time analysis framework. So, we can create all these kind of business rules around what should go into the activity stream, whether it's a new HuffPost Live segment went live, breaking news happened, a new article just hit 25,000 comments, whatever it is, very generic. An API to submit events, Storm to do the business logic, and then OUTBREAK just becomes essentially this consumer of Storm that just kind of says, okay, I have this event in the activity stream, who's interested? Tech stack for Fiji. So we're using Scala and Scalatra for the API. Scalatra, if you guys are familiar with Ruby, is basically the Sinatra for Scala. Just really kind of a lightweight implementation of the serverless API using Scala. RabbitMQ again for a lot of our messaging queue. Storm, which is our stream topology and business logic for analyzing all the events. And then, of course, Outbreak, which is using the Erlang sock.js for essentially pushing all these activity stream events to the JavaScript widget. This is kind of really a high level, right? A producer could be anything into Fiji. It could be a product, it could be a back-end process, whatever it is. We expose a very generic API to submit events. We push that event into the Storm topology. The Storm topology essentially just sort of runs its business logic and says, okay, what do I do with this? So for example, say we want to alert whenever an article hits 10,000 comments, Storm will have a counter that says, okay, I'm going to sort of aggregate on story ID, and as soon as I hit a certain threshold, I'm going to publish an event out to Rabbit. Outbreak is going to get that message and then say, okay, who subscribed to this actual article ID? And again, we're using RabbitMQ for a lot of these sort of message bus behind the scenes between the API and Storm to the consumers. And the idea also here is that Outbreak is essentially one consumer of the outbreak of Storm. It's kind of how we built this, right? So our next consumer essentially, which would be sort of in the same vertical line as Outbreak here, would be something like APNS notifications, right? So maybe users want to get, people I'm sure get like the breaking news alerts on their phone, right? So whenever we send a breaking news alert, we may have an APNS notifier, we may have an email notifier. So the idea was to kind of like separate these flows in the data flow here, and then this right column essentially just becomes consumers on however we want to dispatch messages. And then Storm figures out when we actually have something that's worthy of sending. All right, so let's kind of talk through the mechanics of Outbreak at a little bit lower detail here. So again, I mentioned that we use RabbitMQ routing keys pretty heavily here. So what basically happens is we have this JSON payload that a user sends once they've connected to the WebSocket server. And I'll talk a little bit in a second, but basically it's a 3-node, very simple JSON structure. The first element is the action, the second element is the channel, the third element is the ID. Very simple. We have a channel and ID. So here we have a user that's subscribing to a channel chat room with an ID of 102. So when that subscription comes in, we basically register that subscription in an ETS table. So we say, okay, user has some sort of distinct connection object. We notify the ETS that, okay, chat room 102 has another entry, and this is the connection object. So now this user is connected and essentially registered for this channel and ID chat room 102. Now a producer on the back end sends a message using a routing key prefix.channel.id. So in this case, we just used a prefix of Outbreak for the routing key. So a producer sends a message to a topic using outbreak.chatroom.102 in this case. We then have 2 additional gen servers inside the WebSocket component. The first one is a pub sub server. The pub sub server is essentially just responsible for getting messages off of Rabbit. So in this case, the producer sent this message to the chat room 102. The pub sub server will essentially convert that routing key into a subscription, as we see here. Basically just a tuple, right? Chat room 102. And then what we do is we essentially query the ETS table and say, okay, hey, I just got a message. I've converted this routing key into channel chat room ID 102. Let me do an ETS select on this ETS table and say, give me all the connection objects that actually match this channel and ID. And then basically we just do a broadcast, right? So part of sock.js is we actually can store a special object in ETS that allows us to just call send on it with a payload, which is kind of nice. So literally, once we get down here, we go into like a list for each type thing. We scan through all the results from the ETS table, and we broadcast. So subscribing. Again, a very simple JSON structure that the clients send to the back end whenever they want to subscribe to something. The format of the payload is really simple. Action, sub, channel. Action, channel, and ID. So the action is basically either sub, unsub, or query. Sub is subscribe, unsub is unsubscribe, and query just returns all the list of things you are actually subscribed to. So if you wanted to like maybe show in your application, what things the user was subscribed to, you can leverage query to actually return all the channels and IDs that you're actually actively listening to. Sub, again, just does that registration in the ETS table. Unsub removes your registration from that ETS table. And again, query just returns, everything you're subscribed to in that connection. So really simple JSON structure that we built at the application level that sits basically right on top of the sock.js transport. Again, this is just kind of rehashing. Basically, we store the we essentially just create a tuple and we do an ETS insert whenever the subscribe comes in. Unsubscribes, essentially an ETS delete from the ETS table. Really super straightforward to register and unregister users from subscriptions. So the con object, this is con object in sock.js, and it's kind of nice because we can stuff it in the ETS table, and it allows us to basically just invoke the send method on it with a payload, which makes it really, really easy to just do broadcasting. We don't have to kind of mess with low-level sock.js semantics. When a user subscribes, we stuff the con object in the ETS table with it. When the user wants to receive a message, we literally loop through and just do con send with a payload, and the sock.js mechanics handle the session management and the broadcasting and the connection to the user. So it's a really, really easy way to not have to get too much into the internals of sock.js in terms of sending messages. And again, I just want to reiterate, this con object only lives on one node, right? There's no shared state. So when I connect to server 5. I only ever live on server 5's ETS table, and that URL hashing ensures that my connections always get routed to server 5. So I don't have to worry about the risk of me connecting to server 2 and then having to do a message pass to server 5 and say, hey, it looks like this message is for you. So it keeps that kind of communication very simple. And we'll show in a quick example how we use this to sort of broadcast in a really simple chat room example. Again, publishing. So we use RabbitMQ very heavily right now to handle all of our publishing mechanics. Just quick show of hands, familiarity with RabbitMQ? You guys? Oh, awesome. So, all right, so you guys get it. So I don't have to explain a lot of the semantics there. We use topic for PubSub. So basically when a sock.js or the Erlang nodes connect, we use sort of random queues, and we use a topic. So what happens is every consumer in that setup actually receives a copy of the message. And again, the reason that's okay is because a user is guaranteed to only ever live on one single node, right? So there's no risk in actually doing this sort of broadcast to all the consumers. So again, that makes linear scale very, very simple. So we add a new node to the cluster. It binds to RabbitMQ as a consumer with some sort of random queue name. So we ensure that it gets another copy of the message. The next message that comes in, RabbitMQ sees that user, that box as another essentially queue bound to that topic with that routing key, and it becomes a recipient of the next message. So we could just keep adding boxes using this sort of random queue name, and then we could do this broadcast mechanism very simply. The reason we use topics is we need sort of that wildcard routing key structure. So basically when the Erlang consumer binds to RabbitMQ, we bind as like prefix.hash, and the prefix.hash binding allows us to have this sort of multi-level routing key structure. Again, we're leveraging topics, so all nodes receive a copy by design. That makes this linear scale very easy. We publish to a single topic, basically. So the reason for that prefix is essentially really just a namespace, right? So if you had multiple applications that you wanted to isolate, you would basically have each cluster just bind with a different prefix to a different RabbitMQ topics. That kind of allows you to share the same RabbitMQ infrastructure without having these different applications kind of step on each other. So say you had like a chat application that you didn't want to clobber with, I don't know, a notification application, for example, you would just prefix them differently. So one set of Outbreak consumers would listen on, chatroot or whatever, Outbreak 1.hash, and the other set of applications would listen on Outbreak 2.hash, and the producers would just need to know to publish to the appropriate routing keys. And that kind of keeps, easy segmentation of the applications. So that's kind of why we have like that first node prefix in the routing keys, is really just for like namespacing reasons. And then basically the node subscribe, as I mentioned, the prefix.hash, hash meaning every level of routing key. And again, we use that routing key, basically levels 2 and 3 in that routing key to convert the channel and ID in the structure. That's essentially our mapping. We're using a topic, I believe, and someone can correct me, I believe the fanouts don't support the wildcard routing keys. Someone can confirm. I might be wrong, but I think that's the case. I think the topics have the most flexible structure for routing keys. So what we do is we basically bind with unique queue names for each node, and that guarantees that each node gets a copy of the message. If they each bonded with the same queue name, it would be like a round robin scenario. So to get the broadcast nature, I think when you actually bind the queue to Rabbit, you could not specify a queue name, and it'll just sort of randomize a queue name when you connect. And so that's what we do. You'll see like that crazy AMQP dot, like MD5 hash looking string as a queue name. So every node has its own queue name, same routing key, they each get a copy. So Rabbit basically sees them as individual consumers. All right, so let's just talk through, last bit here is really just kind of talk through an example. We have two users that want to listen to a chat room. We got user A, we have user B, and they're, just for argument's sake, each getting sent to different nodes, node 1 and node 2. So just to talk through what's going to happen in this whole scenario. So they're both going to send the payload to the server via JavaScript over the sock.js channel using this very specific JSON format. And that's it. Action sub, channel chat room, ID 103. The server is going to insert one record to the ETS table on each node with the sock.js session object and the subscription chat room 103. Right? So we have one record on each node in each ETS table. User A right now, for argument's sake, is on server A, and user B is on server B. And they don't know anything about each other. So we have some moderator in the back end that decides they want to publish a message to the chat room. So he will publish a message, or she, to the RabbitMQ topic using a routing key outbreak.chatroom.103, right? The consumer, that pub sub server on the Erlang side, is going to receive a message on the topic with a routing key outbreak.chatroom.103. Outbreak's going to convert that to channel equals chat room, ID equals 103. Each server is going to now do an ETS select for doing a match on chat room 103. And by the way, for performance reasons, one thing we learned, you want to anchor ETS ordered selects in the front. Don't do the wildcards in the front. You get a little bit of a performance ding. So if you're doing any kind of like large ETS scanning on an ordered ETS table, make sure you try and anchor in the front. You'll get a bit better query performance there. So Node A and Node B get a message from Rabbit through the pub sub Erlang consumer. They convert to this tuple. They each do an ETS select for chat room 103 tuple in their ETS tables. Each server is now just going to loop through each connection object, which is size of 1 in this argument's sake, and they're each going to call connection send with the message it got off Rabbit on the ETS table. Sock.js is going to broadcast from node B and node A, and each user is going to each receive the same exact copy of that message coming from two different nodes from the one message that got produced. So some challenges. So this model is good. Some things to note, architecturally, you are kind of bound by the performance of a single Rabbit server. Not really an issue for us. I think performance-wise, I think Rabbit is somewhere in the 20 to 30,000 messages a second range. Maybe it's even higher now. That's probably okay for most people, but something to be aware of that, right now there's no way for a single application to kind of cleanly distribute a lot of that message load. So, monitoring Rabbit took a fair bit of testing, but it's pretty robust now. This is one of the things that we actually really loved about the Erlang side of things. We've killed Rabbit. We've had network interrupts in the data center where Outbreak just lost complete connectivity to the RabbitMQ instances, and it never even blinked. The shutdown got caught in the monitor statement. The Gen server caught it. It threw itself into a reconnect loop very cleanly. As soon as RabbitMQ came up, Gen server reconnected, restarted. We never even touched the application. We've had hard failures. We've had network disconnects, interrupted communication, and Erlang has handled it perfectly every time. It's been really, really impressive. One thing about native mobile clients, you need to use native WebSockets, which works. But Sock.js is its own transport layer, essentially, its own transport protocol. So under the hood, it actually does implement its own version of heartbeats. I think it's by default something like 25 seconds. And the reason it does that is, certainly a lot of corporate firewalls. If it doesn't see a lot of activity over a persistent connection, like a WebSocket connection, it'll just tear it down. So you have to be a little cautious of idle connections. So if you are using a native mobile client, just be wary that you have to implement essentially your own heartbeats. Really not that hard. Sock.js sits on top of Cowboy. So all that means is really writing your own little mini heartbeat route, and then having your native WebSocket client just pull on some timer from, Objective-C or whatever you're using for native WebSockets. I don't know. I've had this here on my slide for a couple presentations now. Making a release sucked, quite honestly. We actually got to a point where the code was like working perfectly, and building a release was, I don't know, for us, just an absolute nightmare. It works great now, but all the intricacies of rebar and rel tool and all that stuff was, I don't know, maybe it's just me, but that was just an actual nightmare for us. But we're over it. We're building beautiful releases now. So we got SockJS to about 100,000 connections on a fairly low core buy. I think it's like around 4 cores. We're probably due to do some better testing on something like 16 or 24 cores. Got latency down to about 1 to 3 seconds. The reason for the variance is, so we use a simple one-for-one gen server for the message passing. So what that means is each combination of channel and ID basically gets its own essentially mailbox and a simple one-for-one. So we spawn the gen server processes dynamically. So the more unique subscriptions you have, the better sort of concurrency you'll get, because you'll have different mailboxes that can process those messages. If you have all 100,000 users subscribed to one channel and one ID, and Alex was kind of talking about some of the downsides, which is probably something we should take a look at, but you are kind of bottlenecked to like that sort of singleton concept, because there's really not a ton of great ways to kind of spread that out, right? All users are subscribed to one thing. We have one process that has to see who's subscribed. So that's kind of the worst case scenario, which is why there's a bit of a range there. Some tuning in VMARGs, a lot of syscontrol tuning to get, MaxCon, TCP backlog, all this stuff. If you guys have done any kind of tuning for high concurrency, you'll know that out of the box, Linux and other OSs are just not really tuned for like max files, TCP backlogs, all this stuff. It all needs to be tweaked. Out of the box, you just won't get anywhere near the performance that you want. Trust me. So SockJS has a major performance flaw that I am proud to announce we actually just very recently fixed. What it was doing is it actually does a lot of JSON encoding when it passages the messages between the browser and the back end. And for whatever reason, I don't know the reason, but basically it was JSON encoding every message. So it would encode a message for every user that was receiving the same copy, instead of encoding it once and then sending the encoded copy of it, which when talking out loud seems incredibly obvious, but for whatever reason it wasn't being done. So we kind of modified that flow a little bit to JSON encode once. We actually shaved about 300 to 500 milliseconds off of latency. The JSON stuff's really, really expensive in Erlang. So we got a really good performance boost there. We'll be contributing that back to the SockJS core. I think there's some more refactoring that can be done in SockJS. There's a lot of message passing that goes on. And we're going to start doing some more investigation about, can we get creative with things like multicast or using things like ports. I was talking at Factory Light in New York, and they were talking about the way, if you guys are familiar, there's an early video product, which is like a Erlang version of a video streamer. They do some of the stuff I think really well, where you need to basically send a video chunk to hundreds of thousands of users. Now, obviously, you don't want to have to copy that same video chunk for every user. You want to sort of broadcast that video chunk to all those consumers. So we're going to look at trying to follow a similar paradigm where we can, basically efficiently, it all comes down to efficient broadcasting, right? And I think there's a lot that can be done to tweak that efficiency there. Again, tune your kernel. These might not even be our actual numbers, but there's a lot of things to really look at. Local port range, SO MaxCon, TCP memory, open files is the first obvious one to go. Just make sure you really spend some time there. VMARGs, increasing the number of processes. Someone corrected me. I thought this was by default something like 4,096. Maybe it's higher than that, but we had a really hard wall before we started touching VM.args. And we couldn't get above like 4,000 to 8,000 concurrent connections. And, CPU was like basically idle, and the Erlang box was just kind of capping out. We really couldn't figure it out. We literally changed these two values, and we went to like 50, 60,000 connections by changing one file. I have to check what the actual default is, but it's definitely too low. So take a look at VM.args. Okay, 1 minute. So last thing, we are going to be open sourcing OUTBREAK. And, we also want to maybe expand the whole concept of Outbreak so that maybe we can use different actual message queue adapters. Right now, we're really bound to RabbitMQ. It would be very cool if we almost had like an adapter API, and if someone wanted to integrate ZeroMQ or even an HTTP interface, it would be really easy to not sort of prescribe having to use RabbitMQ. Something we'll look at. Performance issues, and my last plug is we're hiring. All right. Any questions?
What was the trick that early video used to make sure that the broadcasting was efficient?
I don't know. I think it uses a lot of ports.
Could you repeat the question?
Oh, I'm sorry. The question was, what does early video use to get the efficiency in broadcasting? I don't know. That's something we're starting to look at. I think it uses a lot of ports under the hood, like actual ports to actually handle communication at a lower TCP level. If someone else knows, feel free to correct me, but I'm pretty sure it's at the port level. It's something we just started doing some investigation on. Yep.
You should check out RelX for releases instead of RelTool.
We should check out RelX instead of RelTool. The day I spoke at New York Light, I actually saw RelX, which I was going to actually put in my slide, but I forgot. So yeah, everyone check out RelX if they hate RelTool as much as I do. I don't know. I think it's annoying. Any other questions? All right. Thank you, guys.
Thanks.